Okay, so now that we've looked at the formal definition of an NFA, let's actually look at an example. So on this slide here, we have an NFA that, for simplicity, we've defined over a singleton alphabet A. Okay, so in other words, all of the strings can only be created over a single alphabet A. Okay, and so we have this NFA. It's an NFA because, for instance, here in the state Q0, when you read an A, you can either go to Q1 or to Q2. The other reason why this might be an NFA is because here for Q1, the set of states that you can transition to when you read an A is empty, right? So here, delta Q0 A is a set of two states, okay? So here there's a choice, and then here the set of states you transition to when reading an A from Q1 is empty. And so here, if you're still reading A's, your NFA might jam. Because essentially, it's as if you were telling a computer what to do, but then all of a sudden, your instructions were deleted. And so your computer doesn't know what to do, and the processing of the computations stops, okay? And so what's important actually to note is even though this state is a final state, if you're reading, let's say, AA, so let's say you read an A, then you read another A in here, because there is no transition for when you're in Q1 and you're reading an A, we say that the NFA jams, and so that doesn't lead to an accept, okay? So accepting a string for an NFA means that all of the input string is read, and two, you reach a final state. So I'll just write that as F. Okay. So here we have an NFA, right? And so what we're going to do now is we're going to walk through some of its computations. Okay, so suppose this NFA receives on its input tape the input string AA. Okay, so you'll notice, like I said before, the NFA, once it starts reading the string, has two choices. Either it goes to Q1 or it goes to Q2. So if it decides to go to Q1, right, so it reads this first letter and it goes from Q0 to Q1, okay? Then it has to read the following second A, right? And so it tries to do that, right? But it has nowhere to go in Q1 when reading an A. So the NFA jams. So AA is not accepted using this walk. Okay, so you can think of this as a branching of the possibilities of where you can go to, right? So we know, what I mean by that is we know that we're always going to start at Q0, right? So this is the start. Then when we read the first symbol on the input tape A, we can either go to Q1, right? And then once we're at Q1, we jam, okay? But we can explore the other option, which is instead of going to Q1, we could go to Q2. So what happens if we go to Q2, right? So we start over, we start at Q0, okay? We read the first A, we go to Q2. Then from Q2, in this case, we don't have a jamming state. If we read the second A, right? If we read the second A, then we can use this transition. And so if we do that, we use this transition to go to Q3. And so this second branch of the possible walks that the NFA could take starting from Q0 leads to a final state, right? So we've reached Q3, we've finished the input, and Q3 is a final state, okay? And so what this means is that M accepts this string. So again, like I drew this before, right? So we had said that we start at Q0, then reading the first letter, we could have either gone to Q1 and jammed, or we could have gone to Q2, not jammed, and we could have read then the second A, then going to Q3. We could have also had perhaps an additional transition here that went to an additional state Q4, okay? So maybe if we had done that first, we would have gone to Q4, but then we would have ended the walk in a non-accept state. So a non-accept state. And this would not have led to an accept. But because, again, we can choose, we could have chosen between Q4 and Q3, we could have said, oh, well, actually, what the machine would have probably done, it would have guessed correctly that it needed to go to Q3 instead of Q4. And this is an accept state. And so it leads to an accept. Okay, so this is an example of a string that does get accepted by the machine. What's an example of a string that doesn't? Okay, so in this string, in this input string AAA, we see that if we take this path and we read A from Q0 going to Q1, then we jam at Q1, right? So if we start at Q0, so this is the start, then we go to Q1 for the very first A, then we jam. And so this does not lead to an accept, okay? So then the other thing we could have done is instead of going to Q1, we could have gone to Q2, okay? Then from Q2, reading the second A, we know that we have to go to Q3, right? But then from Q3, reading the other A, right? So we know that we have no choice from Q2 to Q3. When we read an A, we have to go from Q2 to Q3 if we're in Q2, right? So here, actually, there was no choice to be made. And similarly, at Q3, you can't stay in Q3, right? You can't stay here because you need to read the whole string, okay? And so because you need to read the whole string, you're going to transition back to Q2, right? Wait, hang on. So the first string, so this was the first A, this was the second A, and this was the third A, right? And so then you're going to end up in Q2. This is not an accept state, non-accept. And so because in each case, we don't end up in an accept state, we have a reject. And so now I have a question for you. I encourage you to pause the video and try to figure this out on your own. What is the language accepted by this NFA? Okay, so hopefully you've taken a few seconds to think about this. Let's add ourselves on our page so we can talk about it. Okay, so the machine we have has an initial state, it has A goes to Q1, and it has A goes to Q2, and then it has this shuffling back and forth of A's, where Q3 is a final state and Q1 is a final state. So first of all, because we know that this path leads to a jam almost always, what strings are actually accepted via this path? Okay, so in other words, we can ask ourselves, what strings does this part of the this part of the NFA, accept? And so we see that the only string that's actually accepted because of this extra branch here of the NFA is simply the input string A, right? So that's the input string A, right? Because when you read an A, you can either go to Q2, that doesn't lead to an accept, right? So instead, you could read the A and go to Q1 because you end the input, because you end up in a final state and you finish reading the input string. That leads to an accept because you've ended up in an accept state, right? So A is the single string that is accepted from this half of the NFA you can think about. Now, what about this half? Well, what we can recognize here is we have this flipping of the parity bit here, right? So whenever you see a back and forth, one thing that you can think of is the even odd length argument, right? So here we see that if we just look at this small machine here, if you start at Q2 and you read an A, then you accept the string A. Then you read another A and you go back and you accept the string A. Then you read another A and you read another A and you accept the string A. And so what we see here, what we observe is that this smaller machine allows us to accept all odd length strings. So this is odd length strings. Okay, but what you'll notice is that there's an additional A at the very beginning. So to get to this smaller machine that accepts odd length strings, you first have to read an A. And so what you accept then is first an A and then something of odd, right? Okay. So what that means actually is that what you're really accepting has an even length. Because if you have 1 plus an odd number, this will always give you an even number. Okay, and so really what's going on is that this smaller portion of the machine is allowing you to accept all even length strings except for the string with length 0. Okay, so you'll notice that that's why we have this first transition A. What this first transition A does is it stops lambda from being accepted. Okay, so what I mean by that is if you wanted to create a machine that only accepted strings of even length where the length was non-zero, this is the path that you would take. So that means that the language accepted by this portion of the NFA is all the strings that look like A power 2k. So remember, this is just the more compact representation of a string of A's of even length, even because we have an exponent 2k, right? So 2k is always an even number. And so this just means that we have an even number of repetitions of A's, okay? And so the only caveat here is that k has to be greater or equal to 1, right? So this excludes the empty string or 0 number of A's. And so actually what your NFA is doing is it's allowing you to combine accepting the language A and the language containing even number of A's except for the empty string, right? So then the NFA, let's call it M, accepts the union of this first smaller language and this bigger, in fact, infinite language, right? And so this turns out to be the language accepted by the NFA. Okay, and so already you can see that something that you can see one of the tricks or one of the conveniences that an NFA allows you to have is this possibility of unioning multiple languages together and making your machine just choose which one of the branches your NFA should go to accept the corresponding language. Okay, so really what I'm just saying is if you can essentially create a machine that accepts a union of languages, right? There's a caveat on what type of languages these have to be, but each of these languages that are being unioned together, you can create a separate branch for them, right, in your NFA. And this is totally allowed because your NFA provides you with choices, right? So that's the power of the NFA, is that it allows you to create these possibilities, right? To create these choices. Okay. So this is just an example of an NFA, of how to walk through the computation of an NFA, and also to sort of determine based on an NFA what the language accepted by that NFA is.